Okay, so we're going to look at example problem 11.2. This is on page 306. And here we have a belt drive is required to reduce the speed of an electric motor for a grinding wheel as shown in figure 7 or 11.7. That is at the top of the following page. So down here is going to be our motor. And up top here is the grinding wheel. So as you can see, coming out from the motor, they have a shaft, and mounted to the end of that shaft is going to be a sheave, okay? This is what we're going to call the driver, okay? And this is going to represent our omega 1, which is also going to be the diameter of the shaft or the diameter of the sheave on that shaft, okay? Now, there's going to be a belt. We're going to have to determine what that is. And then up on top, notice we have the sheave, the larger sheave, which is called the driven. That's going to be our W2. And it is on a shaft that then is connected, driving at the same speed as this grinding wheel out here. Okay. Now, they're telling us that the electric motor is a 50 horsepower motor. It's rated at 1725 RPMs, and the grinding wheel speed needs to be approximately 600 RPM. So approximately doesn't mean that it has to be exact, okay? But we got to be right around 600 RPM. So we're going from 1725 to 600. They want us to determine the appropriate belt speed and then find the suitable sheave diameters using standard sheaves, okay? And then you're going to select the suitable belt length from the standard table. And then we're going to calculate the corresponding center distance. So this is a very practical problem for out in industry, okay? Where really we're just given where the motor is, what we want our output speed to be, and now you specify the belt, the sheaves, and what the center distance is going to be, okay? So first things first, we're going to pick our belt, okay? I shouldn't say first things first. Actually, before we start picking our belt, let's identify the items that we are given and then the items that we need to find. So if we look here, we're given that our electric motor is 50 horsepower and is going at the 1725 RPMs. Now, as we said, that is our driver, so that's going to be our omega 1 or W1. So here we have W1 is 1750 RPMs. Okay. Oh, I'm sorry, 1725. 1750 is a more common one, but 1725 RPMs. And the power is 50 horsepower. Okay. We're also given that the desired output speed of the grinding wheel needs to be about 600 RPMs. So W2 is going to be 600 RPMs. And I'm going to say approximately. Right. That's a target, if you would. And what we want to find is going to be the belt size. Belt size. We need to find our D1, which is the sheave diameter 1. D2, sheave diameter 2. The belt length, which is capital L. That's the belt that's going to fit over the two of them. And then what the center distance is. Okay, which is going to be the capital C. That's it. Okay. So again, really nice practical problem here. First things first is going to be our belt size. Okay, so step number 1. Belt size, and we are going to use that table, or maybe it's figure 11.4. Okay, figure 11.4. Now, here what we're going to do is we're going to find our faster shaft RPM, which is that 1725, right? It's going to be off of our driver, and then the horsepower. So go ahead and line those two up and see what you get. So if we go over, I'm going to use the 1750 line, okay, just because 1725 is close to that, and then 50 all the way up. So where those two come together, you're going to meet right about there, okay? Now, we are close to a line, but we're close to a line of being smaller, okay? So we're going to stay on the 5V side here. So our belt size is going to be a 5V. So we'll put a little box around that, and we're going to check that one off, that we got that one done. Okay. And if we check what the book got, they indeed got the very same thing. So they got a 5V belt. Okay. The next step that they do here is determine the ideal diameter of the driver sheave. Okay, of the driver sheave. Now, they went ahead and they put their W1 into radians per minute, but let's look why, okay? To get to our ideal diameter for our driver sheave, we're going to look over here first. And what we're going to use is we're going to use a belt speed within the range they gave us. If you remember, we had that slide where it said the optimal speed for a belt to operate at is between 4,000 and 5,000 RPMs, okay? That's belt speed. That's VB, okay? And if you remember, the relationship for belt speed was right up here. So we know that belt speed is going to be the radius of the sheave multiplied by the angular velocity of the shaft, okay? That's why, because we're going to use this relationship here, we need that W in radians per minute, okay? So since our 4,000 to 5,000 is in feet per minute, we're going to keep our angular velocity in radians per minute rather than radians per second, because otherwise we're going to have to go back and forth. So we are going to use that relationship. So let's kind of see how that works. So we know, number two, what are we going to do? This is going to be the it's going to be smaller sheave diameter, okay? And that's going to be D1. We want to determine what that is. So our relationship is going to be belt speed is equal to R1 times W1, okay? Now, in this case, we know that this is going to be 4,000 to 5,000 feet per minute. That's going to be the velocity or the belt speed velocity. And again, the reason being is we're using that guideline of 4 to 5,000 is the optimal range for which you want your belt to be running. Okay, so we're going to specify a number in that range. This radius, okay, is equal to the pitch diameter of our smaller sheave divided by 2. So this is going to be our unknown. Does that make sense? Okay. And then W1 we just need to convert that to, radians per minute. And again, we want it in radians per minute because we're going to have our belt speed in feet per minute. Okay. So the first thing I'm going to do is I'm going to change our 1725 RPMs to radians per minute. So this is going to be W1 is equal to 1725 revolutions per minute. And we're just going to change it to radians per minute. So 1 revolution, 2 pi radians. Okay. Revolutions cancel. So our W1 you get 10,838 radians per minute. Yep. Okay. That's going to be the number we put up here. Okay. And then we're going to pick a number for the belt speed. And to be consistent with the book, they picked 4,500 right in the middle of that, in the middle of that range. Now, I'm going to rearrange this so we solve for D1. So go ahead and algebraically rearrange to solve for D1 in this case. Okay, I'll let you give you a minute to do that. Remember, our radius is going to be equal to D1 over D2, and then we want to solve for D1. And then go ahead and put your variables in. If you get 2 times the belt speed divided by omega 1 is equal to D1. Okay. Then go ahead and put your numbers in. And I'm going to use 4,500 feet per minute, okay, for my VB divided by, and don't forget to multiply by 2. Should get a value for your diameter 1 of 0.8304 feet. Yep, Joseph, you got that. Rainer did. Jacob, awesome. Good. Now, if we look to our chart where we're going to specify commercially available sheaves, these are all in inches, okay? So we just got to convert that number to inches, okay? So I know in 1 foot, there are 12 inches, so feet cancel, and we should get, I get 9.96 inches is equal to D1, right? Now, this is not our final answer for D1, because remember, they want us to find D1, but we want this to be commercially available, okay? So we're going to take this number now, 9.96, and we're going to go down the 5V column. So it's the middle column of table 11.1 on page 303, and we're down the 5V column, okay? And we're seeing 9.96. So we want to do something close to 9.96. All right, we've got 9.7 and we've got 10.2. Now, we're right in the middle of our zone. Remember, we determined this diameter based on 4,500 feet per minute. Okay. If we go a little bit smaller, okay, that's going to affect that a little bit, not terribly much. So you as the designer, you could either pick, see, 9.7 or 10.2. I'm going to peek ahead. I forget what the book picks. They pick, what did they pick? Where's their D1? They have this, they have this. Is that where do you see that?
They just have it written as 10 points.
Oh, they've got it here on the top here. I see. Okay. They picked it right there. So they picked 10.2. Okay. Oh, and then they went back. Yep. So they picked 10.2. I guess they didn't officially tell us. So they picked 10.2. So we'll be consistent with that. But like I said, You could go down a little or up a little, and it's just going to affect that speed a little bit. And remember, that's an approximate. We just picked in the middle of that range, we picked 4,500. And then now what we're going to do is we're going to find out, based on that number, how fast are we really going? So what is the actual based on 10.2? So we're going to redo this calculation, okay? But this time, instead of using or solving for the diameter, we're going to solve for VB. Okay, so I'm going to turn this over. We're going to VB, and I'm going to put in parentheses here, actual, ACT. All right, is going to be equal to D1 over 2, that's that radius, times omega 1. Okay, so now we know that we're 10.2 inches on the actual shiv that we picked off of our table divided by 2 times. Now this again, we have to have in that radians per minute. So I'm going to go back over here, and that was the 10,838 radians per minute. Okay. So our actual belt speed based on this diameter, okay, inches per minute. And then what we're going to want to do is to match up with the book, we want to change our belt speed to feet per minute. So we'll divide by 12 inches in 1 foot. Okay. So our VB, again, actual should be 4,606 feet per minute. Okay. And really what you're doing here is you want to go back and check, does this fall between that range of 4 to 5,000 feet per minute? And indeed it does, right? Right? And again, that's the optimal range for the speed of a belt, okay? And if we compare it to the book, yep, they get 4,606 feet per minute, okay? All right. So now, if we look here, we have our D1, okay? The next thing we need to find is our D2, right? Now, if you recall, using the velocity ratio, okay, we can find our other diameter. Now, we haven't calculated our velocity ratio yet, okay, but we're gonna do that now, okay? So our next step here is we want to find D2, but I guess this will be step number 3. We're going to find the velocity ratio first. So we need our velocity ratio is going to be equal to D2 over D1. Okay. Actually, I'm going to take that back. I'm going to take that back. We got to do one before here. This is going to be our omega 1 over our omega 2. Okay. So for this problem, we know that our motor is going at 1725 RPMs. And we know that we want to be approximately, didn't say exactly, at 600 RPMs, right? RPMs cancel. This is velocity ratio. So we just have to make sure we have the same units top and bottom. And that velocity ratio, if I take 1725 and I divide it by 600, it's going to be 2.875 is equal to our velocity ratio. Okay. This is where our velocity ratio then is going to be equal to D2 over D1. Okay. We know what our D1 is. It's the 10.2. Okay. we want to now determine based on this velocity ratio, what is our D2 going to be off of the chart of standard commercially available shifts. So we want to rearrange for D2. So this is going to be D2 is equal to velocity ratio times D1, which is going to be equal to 2.875. Velocity ratio is unitless times 10.2 inches. This was D1, right? That we just determined. Not the calculated value, the one off of the chart. Okay. So that means that D2, we take the 2.875 times 10.2, we get 29.33 inches. Okay. Everybody follow so far? Now what we want to do is we want to pick the closest commercially available shiv for a 5V. Okay, so I'm going to go back to table 11.1. I'm going to go down this column here, and now I want to find something close to 29.33. Yeah, there's a 27.9.
And when we want it to be bigger, right?
Yeah, hold on 1 second. Closest is 27. Yep. Okay, so what we're going to do is, remember it said approximately 600. So we're going to go, the book is going with the 27.9. Okay, so they're going to go with 27.9 inches is going to be equal to D2. Okay, so that we're going to put a box around. They're going to go with that, but they're going to recalculate the velocity ratio to see where we are in comparison to 600. Okay, so we're going to recalculate our velocity ratio actual now. Okay, it's going to be equal to W1 divided by W2. Actually, no, I'm sorry. We already know our W1 divided by W2. It's going to be D2 over D1. Okay. And now we're going to use these two values to find that velocity ratio. So we have 27.9 inches divided by 10.2 inches. They cancel out. And our new velocity ratio actual is going to be, 27. There we go. 2.735. So that's going to be velocity ratio actual. Make sense? All right. And now we need to find out what W2 is, right? Based on this new value. So we know that velocity ratio actual is going to be W1 divided by W2. So if I rearrange this, W2 is going to be W1 divided by velocity ratio actual. Does that make sense? Okay. So that's going to be, we know our W1 is 1725 RPMs divided by 2.735 unitless because it's the velocity ratio. Okay. So I'm going to sneak it in here. Our W2 should be 630.7 RPMs. Okay. Now, you as the designer would be able to say, all right, the problem said approximately 600. Is 630 okay? I don't know. The book says, yeah, I think it's a little off. I don't know if I would go with that, but that's what they're saying. So they're going with it. Okay. Now, if indeed it wasn't okay, what you would need to do is you would probably then go back to your input. So we picked 10.2. Remember, we were in between 9.7 and 10.2. You could go back and try the 9.7 or the 9.2 to try to get that to be a smaller value and then have your output be closer to 27.9. Does that make sense to everybody? So you'd have to play with it a little bit. They're going with it. Okay, so we'll just go with it so that we can continue to have, answers that are similar. But you would analyze that and you'd say, okay, yeah, 630 is okay, or nope, I need to readjust. But they're going to say, yep, it's okay. All right. So let's kind of catch ourselves up to where they're at. Okay. So they are right here where they recalculated based on that value and they got 630 RPMs and they're saying, yep, we're going with it. So using now what we have specified here, okay, we have specified our D2. So if I go back to the beginning here, we have our belt size and we have our 2 shivs, okay? So we're almost done. So we've got, if you would, 2 of the 3 items that we need for our full drive. As we know, we also need a belt to fit over the top, right? We also need a belt to fit over top. Now, they did not specify a center distance for us. Most often you would have some sort of a target you were trying to hit that would be reasonable, but they didn't. All right. So what they're going to do is they're going to go ahead and they're going to select their belt now. The suggested center distance range is based on the diameter of the input and the diameter of the output. Okay, so we're going to calculate that range and make sure we get the same values as they do. Okay, so if I go up here, this is going to be, I think, step number 4-ish. Okay, so step 4. We are going to use the relationship D2 center or less than center less than 3 times D1 plus D2. Okay, and we have D1 and D2, so this is easy to find. So our D1 is going to be 27, or I'm sorry, D2 is going to be 27.2. Okay, and our center distance is going to be in between then 3 times 10.2 plus 27.9. Okay, so our range then going to be between 27.9 and 114.3, and that's inches on each one of these. Okay. Now, based on good belt design, this is a very wide range, as you can see. Okay. And you'll notice that the midpoint of that range is about 72 inches. That's what they did here. Here is where, again, you would have a better feel for your actual application, what you want that center distance to be. It would be in between those 2 numbers. So they're just picking literally out of the air 72, and that's what they're going to try to hit. Okay. Now, the next thing we're going to do is we need to determine what is the length of the belt, right? So the length of the belt, the equation for that is right here. And notice that we need a center distance, and that's where we're going to first determine an approximate length based on an approximate 72-inch center distance. Okay. And then we're gonna see, okay, is that length on the chart here as a standard belt length? Okay. And once we pick that belt length, because it's not going to be exact, once we picked a belt length that we're going to go with, then we're going to go back and we're going to calculate the actual center distance. Okay. And we're going to see how we compare to that 72. So we're first going to calculate our length here based on an approximate 72-inch center distance. So step number, or continuing on in the step here, we're going to do our belt length is going to be equal to 2C plus pi over 2 times D2 plus D1 plus D2 minus D1 squared divided by 4C. where C equals 72 inches. Okay, C is going to equal 72 inches. Now, this is just copying. This is equation. I'm going to write this here. Equation 11.1. Okay, equation 11.1. And now we're going to put our values in. Okay. So we're going to have 2 times 72 inches plus pi over 2 times, or D2 was 27.9 inches plus 10.2 inches. I'm going to run out of room here. I'm going to go down over here. Plus D2, which is 27.9 inches minus 10.2 inches squared divided by 4 times 72 inches. Okay, so mine's a continue on here. So go ahead and perform that math and make sure that you get right around 104 or 204.9. Okay, I'm going to do mine here as well. Yep. So the overall length, you should get 204.9. Okay. So I kind of broke it out into the 3 sections here, and indeed they do add up to 204.9. Did everybody get that? Be sure you can get that on your calculator. I know it's kind of a long one
Yes.
to put in. Okay, thank you.
I got 2.
Dang it. Yeah.
But
Yeah, if you have the exact numbers here, it should come out. Okay. So now what we're going to do is remember this L is based on a generic 72, just pulling it out of the air, right? Now what we want to do is we want to take this length of the belt. Remember, this is a continuous belt. So they are made in standard sizes. We're going to go to table 11.2 on page 305. And in this 5V section, we want to pick what is the closest to 204. Now you'll notice you have 200 and you have 212. The book went ahead and they went with 212. Okay. You as the designer, again, it would be your discretion on what would make sense for your design. If one was maybe a 200 is one that you put on another machine and you have those in stock, more regularly, you might pick that one. But the book went ahead and they did 212. So that's our actual length. Okay. So L actual is going to be 212, okay, inches. And this is from table 11.2, okay? Now, our last step, and if we go back to over here, we now have the length specified. So the last step is going to be center distance. Now, you might say, well, we already did the center distance. It's 72. Remember, when I calculated the 204, that was having a 72-inch center, right? But now we picked a standard belt. That center distance is going to change a little bit. Okay. What do you think it's going to be? Larger or smaller than 72? I think our center distance, remember, center distance is this. A little bit larger probably, right? Because our belt got a little longer. Okay, so a little bit larger than 72. That's what we're expecting. So now what we're going to do is, this is a two-parter. So we're going to calculate B first using our new lengths and our diameters. And then we're going to plug it in up here into the center distance. Okay, so we'll do this in two parts. Okay, so this is going to be calculating the center distance actual. Okay, so B is equal to, and again, this is equation 11.3. So B is equal to 4 times L minus 2 times pi D2 plus D1. Okay, and again, this B in between is just an intermittent equation. That's all. So that's going to be equal to 4 times 212 inches minus 2 pi times 27.9 inches plus 10.2 inches. Okay. So B is equal to. So you get 736.9 or 7, I'm sorry, 0.779. See, let's look in the chat here. Okay. Did anybody else get 736 point or no, I only did it one time through. 608. Oh, shoots. Okay, let me try it again. Two times. Oh, I know why. I know exactly why. I subtracted. It's a plus times minus. Yep, 608, right? 608.61. Yep. Okay. Sorry about that. I did a subtraction here because I think we did that earlier. Was in my mind. Okay, so now we're going to take this B and we are going to plug it into equation 11.2, which is the center distance here. Okay, notice you have to square the B underneath the radical here. Okay, and then square this quantity as well. So let's go ahead and write out this one. So this one is the center distance actual is equal to, we're going to have B plus square root of B squared minus 32 times D2 minus D1 squared, all over 16. So our number is 608.61. Their numbers slightly are different than ours. Yeah. 4 times 7.
They use the previous slide that it was just 12.
Well, what did you notice? You did the
Their
204.
version is the 204.
They did. Yes. Yes. Now I see. Instead of the 212. Yes. Yes. So they are, and they're wrong then. They're wrong. Yeah. So if you're comparing to the book, yep, you got 75.5. Yep. 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 If you're comparing to the book, because I'm looking, I'm like, wait a second, they got 71.98. But if you look at their B, instead of going with the 212 like they said they were going to, they re-put in the 2.04. So they just, what'd you say?
It just went for-
They went in, yeah. Because now it's 71.98, which is 72, basically. So yeah. So we were expecting it to increase by a little bit, right? Because we went with a longer belt. So 75.5 is going to be our center distance. So that is the last item on our list. So for this problem, like I said, very practical. All we're given is, if you would, a motor speed, what the horsepower is coming off of it, and what is your output about what that you need. So we started by finding our belt speed, finding the smaller sheave, which ended up being a 10.2. Then using the velocity ratio, we found the belt speed, and then we found the larger sheave. And then using that larger sheave, we found the output speed. And this again would be something that you would say, yep, that's okay. Or no, we want to refine that a little bit. And we talked about that when we were going through. Once we have that, then we can pick, it's a long process. We can pick our length of our belt. So calculated an approximate, but then we picked an actual off of our chart. And then once we had an actual, we determined what the actual, I should put an ACT here, actual center distance is using the specified belt from the chart. So any questions on that application? Okay. So that is the second and last example I'm planning on going over today. So example 1, example 2 are going to be part of your practice problems. Okay. But you are ready now to start some of the assignment 6 problems. So what I'm going to do is I'm going to go over to, this was example 1, example 2, and then chains are going to be next. So we will continue on with chains the next time we get together. But if we look at our practice problems here, we did the first 2. Okay, we did the first 2. So so those, you're not ready to hand those in yet, but after our chain design problem, you will be able to. But let's take a peek at the end of our chapter here. And the problems start on page 313. Okay, 313. So I'm going to go underneath my camera again. And the first problem you have, notice it says belt kinematics. The first problem, 11.2, you'll be able to do this one because this is a belt problem. You'll notice you'll also be able to do 11.6, as well as 8. This is geometry, and then this is drive selection 12. I believe that's all of them. Yeah, then it transitions over to chains. So the first 4 problems you will be able to do, which is half of the assignment. Then the last 4 problems are going to be based on chains. Okay. So so for the rest of the time that you have together today, or that we have together today, you'll be able to continue to work. And if you wanted to make progress on this, or if you wanted to look at other homework that you still have to hand in, feel free to do that. So are there any questions before I end the recording here? Okay.
We're gonna figure out the rest of the example problem on, say,
Yes, the rest of these are going to be chain drive. So from 18 through 26 here that are specified, those are going to be, yeah, specific to what we're going to be going over on Wednesday. So right now you're prepared to do the first four, and then after Wednesday, you'll be prepared to do the last four. Okay. All right.